Hello everyone, welcome back to Linked Frequency. In this tutorial, we are going to learn about DC high voltage sensor module design using a resistor network. This is the 8th tutorial of practice project for PCB designers, and I am Vaibhav Sugandhi, passionate PCB designer and technology startup founder. We already see that this kind of a DC voltage sensor modules are available in the market. This is very simple circuit like a voltage divider circuit. However, the modules available in the DIY segment of the market are very limited to the voltage, which is VCC less than 25 volt. You can see that printed on the module itself. The most important thing is these modules consume the power when we don't want to read the voltage as well. Whenever you connect the input voltage, it is start consuming the power. To address these two problems, one is a voltage limitation and another one is power consumption, we are designing this particular module in this tutorial. This tutorial is going to cover a little bit higher level of knowledge in the hardware design engineering when you are doing a project about DIY segment. I hope you enjoy it and I hope you love it. Now let's start with the product development cycle. First thing is black box analysis. We have a high DC input voltage, which is usually in the range of 40 volt or maybe a 60 volt or maybe more than that based on the battery packs and all. Most of the cases in battery packs only. So this high DC voltage will be given to the switching MOSFET, which is a high side switching MOSFET. We call it as a high side switching MOSFET. Why? Because we want to turn on and turn off the DC voltage given to the voltage divider circuit whenever we want it and whenever we don't want it, based on the switching signal coming from the microcontroller. Once this particular switching MOSFET is turned on, we will be providing the voltage coming from the high voltage DC signal, which is a power source, given to the voltage divider circuit. This voltage divider circuit is configured in such a way that it will generate a divided voltage by a means of analogous voltage to the microcontroller. This analogous voltage or analog output voltage is given to the ADC pin of the microcontroller so that we can read and map that particular voltage with respect to the DC high voltage. The principle is very simple, but the tricky part is turning on the MOSFET before reading the voltage and turning off the MOSFET after reading the voltage, so that we can turn off the power consumption of the entire product when we don't want it. And whenever we are looking for the high voltage, these resistive network or the voltage divider circuit is configured for up to 60 volt or more than that. You can do it as per your requirement. And obviously the entire circuit will be having only one voltage reference point, that is a ground point. This is how the black box analysis looks like. Now if I jump into the white box analysis, you can see that 0 to 60 volt DC source can be connected here so that we can make a connector which is suitable for 60 volt of DC. And IRF9Z24 MOSFET is selected for this particular application. Why? Because again, I have referred the datasheet. If I want to show you the datasheet, you can see here. This is the datasheet of IRF9Z24 P-channel MOSFET. Why we are using a P-channel MOSFET? Because we want to switch the signal on the high side, which is switching the VCC segment or maybe VDD segment you can consider. That's why we need to make sure that the high voltage, high side switching MOSFET is a P-channel MOSFET. If you are switching a low side, that is a ground switching, then it is all about the N-channel MOSFET. I hope you understand the basics of electronics here. So this P-channel MOSFET is having a capacity of up to 60 volt DC on the drain to source terminal, or you can say source to drain terminal, VDS it is. And it has a very minimal RDS on when the VGS voltage is 10 volt, a minus 10 volt. It is somewhere around 0.28 ohms, which is almost negligible in our case at this point of time. So considering these two important points, and also very important thing is the current rating. The drains to continuous drain current or drain to source current at the VGS voltage of a 10 volt with a junction temperature of 25 degrees Celsius, it is approximately 11 ampere, which is absolutely greater than what we want. And the requirement what we have is somewhere near to 200 to 500 milliampere at the original state. However, we can go with the 1 ampere of a MOSFET which is having a VDS voltage of 60 volt as well. But right now, for ease of simplicity or for ease of design activity, and also it is available in the TO220 package, I would like to go with this particular MOSFET. Choice is always yours. Whenever you are selecting a MOSFET, just look into the VDS voltage and RDS on should be as low as possible. which is significant as per your application, and also the continuous drain current should be suitable for your application. Considering these three important points and other points in the entire data sheet, you can always rely on this particular MOSFET for this application. Now we'll go back to our MOSFET white box analysis. This is how we selected a MOSFET, and then we will be giving a microcontroller signal to the gate pin of this MOSFET through a resistor and a pull-up resistor and all that thing, so that we can turn on and turn off this MOSFET as when we need it. Then we will be having a voltage divider network with a 22 kilo ohm and a 2 kilo ohm ratio, so that we can decrease the 6 volt or 60 voltage DC into a 5 volt DC, which is approximately or maximum voltage for the ADC pin for most of the microcontroller, which are operating at 5 volt VCC. If microcontroller is operating at a 3.3 volt, then this module is not suitable. So make sure that your microcontroller is at 5 volt when you are using this module as a application node. And obviously we will be having a voltage reference point, that is a reference point for all the entire circuit. Now if I go for the circuit diagram and a circuit analysis, you can see this is how the entire circuit looks like. Again, this is a reference circuit from the online, so that's why you can see the battery voltage is 9 volt, which we are not going to use a 9 volt. Of course, we are having a possibility of 0 to 60 volt, and we are going to give a connector here, not having any battery directly. And this is how the voltage divider circuit looks like, and this is how the P-channel MOSFET looks like. The P-channel MOSFET will be configured on the top side of the circuit, so that you can turn on and turn off the VDD signal coming to the voltage divider circuit. This is how the circuit looks like. Now I'll show you one more important point or one more important thing which you have to use while you are designing these kind of a circuit. That is again one more important site, that is Ohm's law calculator. This site is again not sponsored for this video, but still I love this site and I use it all the time whenever I'm designing the circuits. That's why I'm recommending you to explore this particular site for designing the stable multivibrator as well as for the voltage divider calculator. You can see this is the formula: V out is equal to Vs into R2 divided by R1 plus R2. This is the standard formula for calculating the voltage divider network or the resistance value for the voltage divider circuit. In our case, we have a source voltage up to 60 volt. We'll input that 60 volt here, and R1 value will be 20 kilo ohm and R2 value will be 2 kilo ohm. So if I do something like this, then probably we'll get the output voltage of 5 volts maximum. At the maximum voltage of input voltage 60 volt, output voltage will be 5 volt. If I reduce it to 58 volt, say for example, then our input, the output voltage, which is analog voltage, will be reduced to 4.833 voltage. By looking at the change or the rate of change of analog voltage, we can calculate the source voltage as well. This is how the standard or a typical voltage divider circuit is used in the hardware design engineering. This is most of the time used for the battery voltage monitoring, and most of the time it is used for battery voltage monitoring only. Again, do remember, this is not the efficient way of doing the things. Even though using a P-channel MOSFET to turn off and turn on anything, it is not the efficient way. There are something called a fuel gauges which are meant for the battery voltage monitoring. However, for this particular tutorial, and as we are all beginner in the hardware design engineering, this knowledge is very essential and very helpful for your entire design activity. So if I make it a 54 volt, you can see that the voltage will become 4.5. So it is a linear collaboration or a linear curve between the source voltage and the output voltage which is given to the microcontroller. That is how this entire circuit works, and that is why we need to give this output voltage of the voltage divider circuit to the ADC pin only. If you give it to the digital pin, it doesn't make any sense. If you give it to the ADC pin, then it will give you the all values that is possible from 0 to 5 volt, and which will be represented by 0 to 60 volt of the source voltage. Now this is all about the theory. Let's jump into the easy EDA tool and let's start designing this circuit. We'll go to the file, we'll go to the new and create a project. Here we'll give it as a high DC voltage sensor module. Alright, so description, I'll ignore it as this point of time. So now we'll start with the design activity as we always do with respect to designs. All right. Now you can see that this is how the entire circuit looks like, high DC voltage sensor module. You can see that this connector is a pitch of 5.08 mm because it should be high voltage compatible, kind of a 0 to 60 volt it will be. So you can even write that particular information over here, 0 to 60 volt. So you can reduce the pointer to a 9 pointer. Okay, so this is the 0 to 60 volt DC signal connector, which is of screw terminal connector, and then we have a 3-pin header connector, which is meant for only microcontrollers with respect to ground pin, which has a V sense pin and a V control pin. So this V control pin is connected to the gate pin of the MOSFET, P channel MOSFET, and a V sense pin is the output of our voltage divider network. Whenever you send a high signal or a low signal, it will turn on and turn off the MOSFET. Since it is a P channel MOSFET, by sending a low signal, you will be turning on it, and by sending a high signal, it will be turned off. So when you send a low signal, it will activate the voltage divider circuit, or it will give the voltage from the power source to the voltage divider circuit, and V sense signal has to be sensed by the ADC inside your microcontroller. That is how the procedure for writing a programming for such kind of a modules in the embedded C programming. However, we are not diving deep into the C programming and using of this particular module in real time. Now we'll jump into the PCB designing and we'll finish the entire project. All right. So this is how the entire high voltage DC sensor module is designed. This is the PCB. You can see here the high voltage DC signal will be given with a 1.8 mm of track width. Why? Because it is a high voltage. Current will be very low, but voltage will be high. So that's why make sure that you give a very high voltage track with a track width of 1.8 mm. And wherever it goes, it should be 1.8 mm. Even at the output side also, after switching the MOSFET, the first point of the R3 resistor should be 1.8 mm. After that, once the voltage is divided into a smaller voltage like a 5 volt and all, then you can reduce the voltage track width or reduce the signal track width to be 1 mm again. And wherever we have a control signal and a sense signal, we have created a 1 mm track width only. So this is how the entire circuit looks like, very tiny and a small circuit. Again, these 4 mounting hole are overkilling to it because not necessary this much of mounting hole for the small tiny PCB, which is of like 30 mm by 25 mm or a 30 mm by how much it is actually, a 30 mm by 25 mm. Okay, any two points are sufficient basically. But as a part of the design activity, I have given the 4 mounting hole. There is no wrong in that. And we also mentioned the maximum voltage possible in this particular module. Where should we connect a VCC, where should we connect a ground, and how the output pins are located. All that thing is given along with the module name and a hashtag link to frequency. This is how the entire circuit design has to be done. And this is how the 2D diagram looks like for the product, and then the 3D diagram. Luckily in this particular thing, we have all the components majorly. Again, capacitor is missing, but you can see again, we have followed the IPC standard. We have kept the MOSFET on the board edge so that we can add a heatsink if it is required. I don't think so we need a heatsink for this particular project, but still, if you want it, if it is heating up because of a high voltage fluctuation or a high current flowing or something like that, then obviously you can add a heatsink here. So this is all about our designing the high voltage DC power supply based the sensor or maybe a module which is essentially used for battery voltage monitoring and all that thing. So I hope you enjoyed the entire project. I hope you learned something new by using a MOSFET as a switching device in the battery monitoring circuit. Again, I'm telling you one more time, this is not an efficient circuit in case of a battery monitoring system, but this is the one of the most widely used DIY project or a mid-range design and development circuit used in most of the projects or most of the product that we are using in nowadays options. The better or the efficient option is using a fuel gauge, which is not an easy method, and it uses the I2C for sensing the signal from the battery voltage and all that thing, which we are not going to talk right now. So I hope you enjoyed the entire tutorial of designing a high DC voltage or a DC high voltage sensor module using a resistor network. Thank you so much for watching the video. Consider subscribing to our channel Linked Frequency. Practice all these projects to the fullest extent so that you can master the skill of hardware design engineering and you can crack the interview that you are appearing for the next 1 month or maybe more than 1 month. So thank you so much for watching. See you again in the next video. Until then, tune yourself to make a difference.